Okay. Hi, everyone. Today my name is Josh Persi, and I will be presenting chapters 14 and 15 of Klaus Wilke's book, The Fundamentals of Data Visualization. Chapter 14 is on visualizing trends, trend lines, and chapter 15 is on visualizing geospatial data. So there's not a lot of continuity between the two chapters. They kind of cover different topics with different concepts, but I think we are ready just to dive right in. I will preface this with I feel like these chapters maybe kicked it up a notch in complexity and detail from previous chapters, at least the ones I've led. I feel like the last one I led was on visualizing something simple like bar charts or proportions. Whereas here, visualizing trends and like time series analysis and then visualizing cartographic data, people make their whole careers on like one of those topics. So they're very deep. They require a lot of background, even to get data ready to visualize them. Um, so I struggled, I think, in both chapters to pull out like the key principles I should keep in mind when I am graphing, but excited to see if you guys kind of took more away from it than I did. Okay, chapter 14, visualizing trends. By the end of from this chapter and from this slide, I hope you will be able to understand how to create smooth trend lines by transforming the data into something smoother, by applying smoothing functions, by applying like defined classic mathematical functions, and by transforming the axes of the plot. I also hope you will understand the basics of detrending a time series. Um, just to make sure I understand how this works, you guys aren't seeing your faces on the screen, right? I see a little Zoom pop up with all your faces, and is that getting captured in the screen share?
No, we
Oh,
just,
okay. Okay, cool. I think we're good then. I think it's just something that pops up for my view, but you guys are just seeing what you're supposed to see. Okay, so something that the book doesn't immediately mention is like, why would you smooth? The main point, I think, is to make your message clearer um, by reducing noise. Essentially, that's what a smoother does. But smoothing only makes sense maybe if you are, depending on the message you're trying to tell. If the message you're trying to tell here is that um, on average across this time series, the line went up, like maybe you could smooth quite aggressively and still convey that message. But if you're trying to tell a story about the dip in whatever that is, March 2009, any amount of smoothing is going to make that less apparent. So you might want to not smooth in that case if your point is to emphasize that dip. The first way the author mentions transforming data is by doing a moving average, by taking an average across a moving window of time. It could be like 20 days, 100 days, presumably other units of time, weeks, months, years. And what you're doing here is you are averaging the value across that window, and you're moving through your time series. So a product of that is that you have a shorter time series because you are kind of losing the information on the far ends of the axis because they're being averaged up. And that's shown here by a 20-day average, which is the smallest window of the three shown here. It covers most of the original data, but a larger window, such as the 50-day or 100-day, covers a shorter. The smooth line appears shorter because the size of the window the average is taken over is larger. Honestly, I don't know if this is uh, kind of flagging me as a amateur, but I've never really used moving windows. I always just like aggregate to the next highest unit of time. So like if days were too noisy, I would aggregate to weeks. If weeks were too noisy, I would aggregate to months, depending on the outcome. But that's how I've always approached kind of smoothing. The nice thing about that is if you have like complete chunks of time, like a full month, a full week, you don't shorten your trend line. You have a trend line that exists, I guess, for the whole range of your new data. But I don't know if that's bad form or anything like that. Feel free to jump in. Oh, I see a question in the chat, or you see the world through the same window. Okay, thank you, Arthur. Thanks for the sanity check. I don't know how the data science learning community feels about it, but you are welcome to interrupt me at any time.
The moving window, the way that I've used it,
Mhm.
it's not really with data like this, it's more with geographical data. I don't know if you're going to cover that later on the other chapter, but a
Don't
moving
think
window
so.
with geographical data, what you do is you aggregate pixels. Because if you have like a 1 kilometer pixel, then you can go by 5 kilometer pixel, like you go to the next ones. So I've seen
Oh,
it used
interesting.
more like that. Yeah, with geographical data. So I think moving window, it's not just used here, just to keep that
Okay.
in mind. Yeah, with data.
What's
Yeah.
with the geospatial angle? Like, what's the end goal to like smooth
Yeah, because you have
the
too much
point values?
detail and you want to aggregate the data because you want to see, for example, um, by county level or something like that. So you need to aggregate data because it's too fine scaled. And you want to do like, for example, I'm trying to think of an example. If I can think of one, I can put it in the chat, but it's more because you're working with something that is too fine grained, like the pixels that you have, the resolution is too small. So then
Mhm.
you want to aggregate more data in order to smooth, right? Like because
Yeah.
we're seeing smooth the data so that it's not like so finely grained. If I can think of an example, I'll put it on the chat. But yeah,
Okay.
yeah, just
Cool. Same idea, I suppose, just like creating something that's smoother, just across a different type of data. All right. Awesome. Thanks, Gabby. So that's what I call, perhaps incorrectly, smoothing by transforming the data. Something you might do before you actually get into plotting. You might calculate your new aggregated average. Um, then there are things that, at least in the ggplot2 and our world, I apply by like functions you call with, say, like geom_smooth. And these are I pronounce it as Lois. I don't know if that's correct, but the local, I forget what it stands for, the local something estimation smoothing. I can't quite remember the acronym, but it basically fits a bunch of local low level polynomials, I believe is the term used in the book, to your um, to your line, creating this smooth look. Um, it works basically out of the box. I don't know if anyone here has ever used geom_smooth. Um, I'm not even, maybe the default smoothing function is a linear model in that, but it's not hard to set up the lowest smoother and it produces good, attractive results. You can adjust how it looks through parameters that I believe are similar to like a bandwidth, um, which might ring a bell from like plotting density plots and kind of like histogram bins. Like you can get a smoother or a more wiggly line depending on how you set these parameters. So there's a bit of like, maybe that's one area where like the data viz is more art than science. Like you just fiddle around with a bunch of values and see what fits your data well. Um, Another technique was splines, which I've never used before. Apparently there are many kinds of, I guess, I don't know what the right term is, distributions or functional types of splines where you can get pretty different looking results from the same data if you just specify a different functional form. The book didn't dive into too much detail here, besides from naming some like Gaussian and a couple other ones with names I can't recall. But you can basically, with any function that kind of automagically smooths your data, there are parameters or things you can tweak to get pretty radically different looking smooth lines. And that's why I think the author didn't say this specifically, but like plotting a smooth line without the raw data underneath in some capacity is probably asking for misinterpretation. And there's no way to like assess how well that smooth line fits the data unless you were to provide additional model fit statistics, but even those can be misleading, as shown by like Ascombe's quartet. Okay. What the author said is that it is preferable, wherever possible, to apply a defined function, whereas those smoothing functions, as I'm calling them from the previous slide, the Loess and spline functions, they kind of just, when you call them, they take your data and figure it out for themselves and then plot the results. In this case, typically, at least I think I would model the data first using the equation. So here it's an exponential equation that exponential model that he's used to define this smooth line. And I think that's good because most people kind of naturally understand what the shape of an exponential function looks like. And this applies for other somewhat common functions like a linear model, a straight line, sigmoidal model, an asymptotic function, things like that, that maybe are covered in a high school math class. So he is a fan of this, and I am too, just for explainability. Like I couldn't explain how a Loess smoother exactly got its curved line, but I could probably explain to a stakeholder or something how we got an exponential function. I think that I agree with the author. Using a defined function is great. Rarely do I have data at my hands that so nicely follows an exponential model. And then you run into things like, how do you know your model is actually like appropriately fitted? Do you get model statistics like an R squared? I think that only applies to a linear regression, like a straight line model. But whatever function you use, like how do you show it's a better defined function than a different equation, is something I don't know the answer to. And then the last way to smooth, I gleaned from the book, is you can smooth by transforming axes, by taking the log of one or both axes. Log transforming seems like something of a mystical art to me, because I don't really understand how it always produces, not always obviously, but many people say just log transform your data and it makes messy data that's not linear into a straight line. Seems almost magical to me, but maybe that's just because I don't have a great grasp of the math. But he says that you can take that same data I just showed with the exponential model fitted to it. You can log transform the y-axis here, and then you get a straight line. He says that it's preferable to fitting the model with exponential data and then showing it. Oh, sorry. So he says fitting a linear model on log transform data is preferable to fitting an exponential fit, because I suppose the exponential equation. This might be some general issues it has with overestimating data on the like kind of asymptote towards the y-axis, like the origin point. Because as you can see here, the exponential fit model overestimates the value of preprints per month compared to the actual data. And I think I understand what he's saying here, but also if you show this to me and ask me to understand how preprints per month changes, I would have an easier time understanding this graph that's not log transformed and shows a fitted exponential model than this graph that shows a linear model on log transformed data. But I think that's maybe more of my difficulty in interpreting log transformed data quickly. Okay, then he very briefly talks about detrending time series. And I struggled here because it felt like a very surface level treatment of something that people have written whole books on. And from my attempts to detrend time series seems like quite a complicated thing. But basically, for any time series, there are probably multiple components to it. There's perhaps a long-term trend, such as is like the value increasing or decreasing, kind of almost as a like a larger scale force. Are there seasonal patterns? Are there cyclical patterns that repeat over time, but not in step with seasonality? There's random noise, and then there's your actual phenomenon of interest or phenomena of interest. So as far as I understand, detrending means you basically want to remove everything you don't care about and just be able to plot your phenomenon of interest and see how that changes over time once you've basically accounted for long-term trends, seasonal patterns, and other components of the time series. He shows that you can break down the Keeling curve data or CO2 concentration in the atmosphere over the last couple of decades. You can break it out into a cyclical component. So I guess that's a monthly average, a long-term trend, seasonal fluctuations that correspond to like summer, fall, winter, spring. And then you have the remainder. I would have to go back and double check the graph. Yeah, it was a little hard for me to follow in this part, but I'm not sure if the remainder is what he is calling the noise or stuff that has been left over after the noise has been taken out. But basically, that is what I took away from this chapter. I thought it was pretty high level. I don't know. I'd be very keen to hear if you guys took away more from it. But I struggled to find like key points that I could jot down in my notebook and refer to the next time I make a time series graph. But if there's nothing there, we can go on to the next chapter and have a discussion afterwards. The next chapter is totally different. We're leaving trends behind us, and we're talking about visualizing geospatial data. Again, a pretty high-level treatment of the topic, I think. Struggled to find some key concepts, so let me know if you have any. But what I think we can get out of this chapter is an understanding of the key concepts in geospatial data viz, including some terminology like what is a datum, what are projections, coordinate reference systems, and why do they matter when visualizing data. And we can identify some choropleth maps and their variants. The Earth, I think this is like often repeated by people who care to make the distinction, but the Earth is not a sphere. It is a oblate ellipsoid, which means it's protruding more around the equator and it's slightly narrower at the poles. As far as I know, no one knows the exact shape and size, like at a very high resolution of the Earth. So we model it with something called a datum. There are several datums. The most common that I've seen is the WGS World Geodetic System, 1984. I believe it shares an origin with like global positioning system, GPS technology, and it is commonly encountered on the web. Like if you are using a interactive leaflet map, for example, I think they're often, well, they're actually not in WGS 84, but they pull from, I'll stop there because it maybe gets confusing, but okay, great book recommendation, Arthur. I'll have to check it out. I would also like to dive into a book that maybe treats more heavily on geospatial data viz, but as I said, this one's fairly high level. But to continue on with datums, there are apparently other ones. I've seen NAD83 out in the wild, so to speak, for North America. Apparently, an ITRS datum exists for higher precision modeling, but WGS 84 is, I think, what most people will have their data in when they're trying to data visualize it, at least at the start. It's what data often comes to you in. So that's datum. How do we model the Earth as a 3D object? Projections are really how do we model the Earth as a 2D object, because we have to unwrap the 3D surface of the Earth into a 2D projection that we view on paper, in a book, on a screen. All projections sacrifice something, either size, shape, or both. Because the Earth is a sphere, you can't unwrap it and preserve everything all at once. So because there's this like inherent trade-off, there are 1,000,001 different projections you can use for different areas of the world and for different concerns. So if you need to prioritize faithful representation of space, you might use the equal area projections for your area of interest. But if you are more concerned in like the shape and the form, the coastline of a particular place, you would use a conformal projection. Various types of projections have like come and gone into style over the years. Mercator was very popular and is still used in leaflet as the web Mercator projection. If you are often plotting global data, the author makes a recommendation for a particular projection, the global geode good. I don't know how to pronounce that word. Homolocine. Pronunciation might be off there, but you can use better projections than Mercator nowadays, according to the author. But the exact projection you want to use will vary based on where in the world you're trying to plot. So I often plot data from Canada, so I use a different projection than maybe someone from Australia would use. Well, almost certainly I use a different projection. And I found that if you're making a plot for a particular country, I typically default to whatever the National Statistics Agency of that country uses. I think Canada uses like a Lambert conformal conic. Statistics Canada uses a Lambert conformal conic projection. So that's what I've been using in my work. But there are places to go to find out what projection is maybe the de facto standard for a particular country. When it comes time to actually plot your data, you want to plot it in layers, most likely, if you want more than a simplest graphic. There are several layers, and just like in other plotting softwares that use kind of a grammar of graphics, you have a layer of things and you plot one on top of the other. So you often start with a terrain layer, or maybe not necessarily terrain, Could be like street map. Maybe I'll show you. There's something for leaflet that shows a bunch of different base maps is what I call them, but some of them show actual terrain. Some of them show satellite data. Some of them show just like stylized versions. If you wanted like an all dark look for your map, you can go through, choose one from various different sources. This is not the only place, but getting that data into whatever graphic visualization software you're using will probably vary. But you pull that in, you set that as your base map. Then you can add your geometry layers. So these are things like your points, your lines, your polygons, your multi-polygons. Kind of a different world, but I would also consider like rasters in this vein as well. You're plotting some sort of spatial data. This is just another type of geometry he's preparing. And then you can do markup. You can write annotation layers for it. So you can add labels, you can add scale bars, and north arrows. One thing I found out when plotting a conformal projection, so one that preserves the shape as opposed to the size, and you go over a large latitudinal area, so say the Americas, using a scale bar is kind of meaningless because the scale bar doesn't mean the same thing at every latitude because you're using a conformal projection. Area is not preserved. So the area is different between high and low latitudes, or extreme and equatorial latitudes. So his suggestion that you should always use a scale bar, I think applies if you're doing a equal area projection, but maybe not if you're plotting a conformal projection over a large latitudinal area. It probably doesn't matter if you're plotting like an east-west extent over a small latitudinal area. And then he talks about choropleth mapping. Choropleth maps, they are common. Commonly used to show a value as a density relative to a certain polygon geometry. Here, I think this is counties of the US, and he's showing the population density. The author says that you should scale your values by the size of your polygons. And I think that makes sense to me, but I have definitely made the mistake of just plotting the values and not standardizing by the size of the area. Don't know if others have done that, but something to be mindful of. Here he's showing dark values as the higher intensity and lighter values as the lower intensity. That works well, particularly when your background is white, as the background page of this screen is. You can also do the inverse. You can make the light values the high intensity and the dark values the low intensity. It only works with particular color palettes where you kind of perceive, like maybe I would say like somewhere on the heat spectrum of colors, like the reds, the yellows, the oranges. So it makes it seem like the higher intensity values are glowing almost. And this is particularly useful, he says, when you're, I can't show it here, but when your screen is dark, if you had like a dark mode on your web page, the lighter values would pop more than the dark values, which might fade into the background. The author makes a great point about Alaska and whether it should be shown in its true size here. So this is a con or an equal area projection of the United States. So the lower 48, Alaska and Hawaii. And Alaska is, I can go back. Alaska is often shown much smaller in this kind of graphic. The author spent considerable ink saying that he's not a fan of this, but that he really likes it when you show Alaska true to its size. So you can see that Alaska is a behemoth of a state, and it is not actually smaller than Texas, but is bigger than Texas. Maybe
Ironically, I think he is at University of Texas, so I don't know
Oh.
how well that went over with colleagues and
Yeah.
yeah. Sorry.
No, that's a good introduction. Yeah, hey, the big Lone Star State getting trumped by Alaska here. I found much of this chapter like U.S. specific, which is maybe it's not a dig, but it's just a lot of these conventions really, I've seen at least through like viewing Tidy Tuesday and other places, really only make sense when you use the United States. I'd be keen to know if anyone else has like done this kind of like moving around things with their own national.
But you know,
What?
it also comes in when you're comparing regions on different parts of a continent. So if you start thinking about the US, and then when you think about South America, they usually show how massive the United States is, but then because of the projection that they're using, South America sometimes looks smaller, when in reality, sometimes it's even larger. Or compared to Europe, it sort of looks like South America and Europe are kind of like the same, have the same area. When you start really to put things in the right projection for each area, then you realize Chile is, even though it's very skinny, it's massive compared to the other ones. And then you put Brazil next to them and you're like, yeah, I mean, with all due respect, the US is not that massive compared to other places, right? So I think that we can also see let's say, apply that same principle when we start to compare across regions or across countries.
I'm not sure if you guys have seen this. It's been a while since I've been here, but uh, it's relevant, and I think it's a good thing that I haven't mentioned yet. How does this work again? So yeah, the United States.
Remember to put the link on the chat because this is
Oh, thank
beautiful.
you. Thank you. I'll do that right now. So takes me a second to remember this, but okay. The United States, if you project, like if you put it, how do I express this in words? I'm kind of spitballing here. The United States looks that big because it's at that latitude, but if you put it at the equator, it would be like the size, roughly, maybe a bit smaller than Brazil. Maybe a more pronounced example would be, so where's Greenland? How do I do this? I can't quite remember it. It's been a long time since I've been here, but you can play around with it. I think it's a good tool to like interactively show how a projection like this, I don't know which one this is, maybe Mercator.
Put it with
how
Australia. Yeah, on top.
Sorry, put this one.
Yeah, the
The US and
US
Australia.
on top of Australia. Yeah.
Yeah, like roughly same size to my eye. Greenland is obviously a massive one because it's such a extreme latitude that it looks bigger than, or at least as big as Africa, but if you bring it to Africa's latitude, it's like, I forget how small. It's much smaller compared to Africa. But sorry, it kind of just popped up in my head. It might be interesting if you need to convince anyone of latitudinal skew kind of in perception of sizes.
Yeah, no, that was a beautiful resource. I'm glad you shared with us. Yeah, I think that's exactly what I was talking about. And sometimes the projection that you use skew exactly that, right? So yeah, perfect, Josh. Yeah.
Good. There's all sorts of like, I guess, history behind it of like North American, European map makers made like their countries look bigger and equatorial countries look smaller. And I think that's just like a legacy thing that we are still grappling with today, those like early decisions and biases of European, North American map makers. Anyways, to continue on with choropleths, which many people say is chloropleth, like chlorophyll, the plant molecule. And people who know the difference will like 100% of the time correct you and be like, it's chloropleth, not chloropleth. But I've definitely said chloropleth before, so no hard feelings either way. Sorry, Gabby, you're
I
muted if
can't
you were.
hear the difference. Say them again, like the correct and
Here,
the wrong one.
maybe I can. This is like a pedantic thing that I've seen people. So chloropleth is, I think, how definitely I started saying it, and people say it sounds like chlorophyll, like the plant molecule.
Yeah.
But it's choropleth. There's no L in it. Yeah. But that's often just a thing that people who like care about that kind of word play will be like, actually, it's choropleth, not a chloropleth.
No, but that's a good, also that's a good like what is I don't know what to say, correction or whatever, because yeah, I mean, how do you pronounce it, especially for people like me that are not, English is not my first language. I think I've been saying chloropleth. You're right, and it's choropleth, I guess.
Right? Well, there you
I
go.
feel like
Maybe,
most people go through that. But I also used to say chloro, and then I realized it's coro.
Choro,
yes.
yeah.
Yeah, it's almost like a rite of passage for anyone who spends a substantial amount of
Yes.
time plotting. You start out saying chloropleth, and then you go on to choropleth, and
Yeah.
you tell everybody about it, as I'm doing here.
Oh, thank you.
Good. So to continue with choropleth maps, the author says that quantitative color scales are hard to interpret because what exactly is that brown correspond to? Is it 0.01? Is it 0.05 or some value between 0.01, 0.01 and 1? It's a little hard to get exact values. He says you should bin them into categories like this, where each color kind of uniquely identifies one bin. It's much easier to visually match up the colors with the legend because there's only 5. There's not as much variation. I'm a fan of that. I think it's a good idea. And then we have Alaska being massive down there. Oh, I forgot how to work this. So then he goes on to talk about what I think of as choropleth variants. A cartogram, I think it looks very odd. I don't know if I would ever use one like this. I have also really only seen this used for the United States, particularly the lower 48. I feel like just because it's such a recognizable like landmass, and I feel like people who have never been to the States know at least like a few of the states. So you can do this basically in an attempt to, I believe, match area. Is that right? I don't think that's actually right. Why do you use cartograms? Let me go back and. Oh, so he's using it to scale for another variable, I think, modified to proportional number of habitats. Okay, so it's not area because Alaska looks way smaller than Texas, which wouldn't make sense if you were preserving area. But Alaska is far more sparsely populated, so it shows up as a smaller, much odder looking graphic than Texas, which is fairly populated, from what I understand. Again, I have a hard time reading it. I don't like it that much, I'll be honest. Maybe there are use cases. Let me know if you have any. But another variant is another type of, he calls it a cartogram heat map. I think it's super cute. It makes me think of the periodic table. Very attractive. And I think it functions pretty well as like a piece of data visualization to convey a message that Alaska has higher median income.
Yeah, as New
But it's
Jersey,
more specific.
Connecticut, and Maryland, yeah.
Yes, but I guess you lose out on that inform. I guess one of the reasons why the cartogram here, as opposed to the cartogram heat map, might be preferable is because you get to see that Alaska might have a higher median income than Texas, excuse me, but it's way smaller. And that's what the like size of it is trying to convey. Whereas here, size is kept constant, so you lose that little bit of nuance that
Yeah.
Alaska has far fewer people than Texas.
I think so with the first one that you showed, I've seen it done a lot of times. And for example, with human footprint, or the carbon footprint, things like that, that the UN usually does those kinds of maps.
For global, like
For
all
global,
countries?
for example,
Okay.
yeah. So when you want to show, the thing with that is that you need to, I can put the link actually, because I just
Yeah,
taught
please do.
that, but I can put the link with that. But the thing about that is that you really need to know, or you have to put maybe an original map so that, or your public has to know how the country looks or the region looks like originally, so that they can say, oh yeah, now I see that the Texas is a little more inflated, or how much more inflated it looks. So you need to know like the roughly the original shape. That's not necessarily the case, because I may know that about, let's say, certain countries in Europe, America, I do know it by heart. But if you say compare Algeria, for example, I don't have that at the top of my head how that looks like
Yeah.
originally. So I think that's, yeah, you're assuming a lot, but it's super useful if you're talking to educated people that actually do know those things. And then the other one, the one that looks like the periodic table, I love it, but I'm gonna be honest with you, and I think that maybe let's go on a hunt for that. I've only seen it done with the US map. I have never seen
Totally.
this done
Me
with
too.
Canada, with African countries, Europe even. I haven't. So I think Central America would also be easy because we all follow like a straight, well, not a straight line, an angle line, but we're all like one after the other one. So that is something that I would like to see an example of, and maybe I should write a
I got
post
the
about
link.
my blog or something. But yeah, how does that translate to other regions?
Oh, Arthur just linked. Arthur, do you want to? Is this? Oh, okay. I don't. You can share your screen if you want.
Yeah,
I don't
no,
need to.
you got it.
Okay.
I don't know if this is the exact one. I remember seeing something like this in the past, and I think they had
Europe.
there's some way that you could use the package to create your own, which to me was always an appealing idea, but I'm sure that it's a lot harder than I would involve more effort than I would want to put in, I think.
So this is from the documentation of that package that
Yep.
done?
There's another one too, and I may be mixing things
Yeah.
up. I was just kind of Googling as we were talking because this discussion reminded me of stuff I'd seen in the distant past. There's another one called GeoFacet, which is a little bit different. I think it preserves this idea of having boxes for geographical entities, but then you can populate. So basically, it's a facet. So you can populate that grid space with other how do you call it? Like other visualizations. So if you
Like
wanted to
other
have
graphs.
a line chart, for example, you could do that.
Yeah, like I think there's one.
Oh, actually, that's coming soon. Sorry. Never
Yeah,
mind.
yeah. No, but that's a good reminder, yeah, or a good segue.
To say one other thing about
Like,
these
yeah.
cartogram heat maps, I think you could create them for other places of the world, but like, do you have enough cultural mind share to like show that to someone and they'll be like, oh, I intuitively know what this means. I feel like even if you showed this to someone who doesn't really spend time in the Data Viz world, they would still be like, oh, I get it. It's like, it's the lower 48. And then you got Alaska and Hawaii over there. And like, just because of how recognizable the US state boundaries are, and how often this particular type of graph is used, I feel like it's just very, like you can share that graph with almost no problem and people will understand it in the context of the US. But if you try to do the same for Canadian provinces and territories, I don't even know if a Canadian would like immediately grasp that layout.
Mm.
But then the last type of choropleth variant is an extension of the cartograph heat map, where you're using facets, just like Arthur was talking about, to locate the polygon, or rather the name of that polygon in its relative location to all the other polygons. And then you plot some sort of data. Here it looks like a density plot of unemployment for each state, and the state facets are located in their approximate location in like a map of the contiguous or continental United States. So obviously California is in the bottom left, Maine's in the top right. It works, I suppose. I feel like it's still just a lot of facets to look at. And the nice thing he says about this is like that this cartogram is that states are bundled together, so you can kind of see that, like, you can kind of see some patterns. Like, I don't know what New Jersey, Maryland, Connecticut, I don't really know much about those states at all, but they all seem to have higher median income, and maybe someone with more knowledge of the states can be like, oh yes, those are all this kind of state, or they all share this attribute, which explains their higher median income. And you can do that to an extent here, but it's still hard to process this many facets, at least for me.
Yeah, I think with that one, I do like this last map. The only thing to remember is you can use color as a third categorical variable. So if you want to identify like regions, for example, or if you want to highlight
Nice.
a few specific states, you can use color for that. The other thing is that all your scales, Y and X, must be exactly the same. Otherwise, you won't be able to compare them. So if you see, all of them go from 0 to 15%, and then the x-axis all go from 2008 to 2012, I suppose. So then that because it's so easy to, forget those little details, but I do like them. But I agree with you that it's like you have to process a lot of information at a glance. But I don't know. I love those graphs.
They're cute. They're very nice. I think that's the end of chapter 15. We've got about 7 minutes left, I think. Does anyone have thoughts that they would like to bring up about these chapters?
I wish there was more geospatial.
I'm with you on that. Maybe we'll have to do a follow-up book club after this one.
Yeah, actually, we should do that. We could
I'm
do, I
having a
don't
good
know.
time, so I'll keep the party going.
Yeah, I think this one, the one that you posted, Arthur, the GeoComp book, I think that's been read before, right? Here at DSLC. And I
I
don't think,
think yes.
yeah,
But it's kind of, it seems like it's a mix. I mean, I guess as well, it should be like a mix of, let's say, like the data munging part of geospatial and then the mapping part.
yeah.
It seems like it's an overview and it doesn't go too, well, I don't know, on like, it doesn't go too deeply on the mapping part, and then makes some opinionated choices about the mapping packages to use. But anyway, that's maybe like a small niggle, perhaps. But yeah,
There is,
I just wish I could go deep on, perhaps I'm wrong on this, but go really deep on ggplot maps. Yeah.
so, ggmap, I don't know if ggmaps, but there is a book that we were reading. Oh my God, I started that cohort, but I don't think I finished it. But there's another, I don't know if there's an active cohort right now, but we should go into the DSLC, all those hashtags, all the channels, and see what geo books they have, because I do believe they had one, but I don't remember which one it was. I think, oh, it's the same one that you posted. Oh, I thought they had another one too. But anyway, so if there's not an active cohort, then that means we can start another one.
I'd be down. Arthur had to drop off. I'm not sure if that showed up
Oh,
for you,
okay.
but should we
Keep
be
going.
hitting stop in the message as well this time?
Yeah,
think
I think
so.
I'm gonna